Hey guys, Kenna here. Today we're going to be looking at electric fields. Now we've talked a little bit briefly about electric fields in some of the notes before, but today I want to go ahead and focus on them. Now, we talked a little bit last term about gravitational fields, but we never really gave it a lot of thought in terms of how they worked or how they functioned. We just said, oh, and then you're in a gravitational field, and so you experience gravity. So today I really want to go ahead and talk about what a field really is, and in particular, what an electric field is and how it's created. So let's go ahead, jump right in. We'll take a look at the essential questions and kind of go from there. Question number one: what is an electric field and how is it created? I mean, what exactly makes a field exist? Number two: how is direction determined in an electric field? We'll be kind of specific about how that works and how we do that with test charges. Number three, how do you calculate field strength and what is the unit that we use? And lastly, how are voltage, current, and the electric field related? So we talked a little bit about the fact that in electricity, it's different than gravity because gravity is only an attractive force. But in electricity, we have both an attractive and a repulsive force. And it depends on what the charges are that are interacting with each other. So the attraction and repulsion of charged particles occurs because the charged particles have electric fields around them. An electric field is an area over which an electric charge exerts a force. And we're going to be able to use Coulomb's law from last class to be able to talk about how to calculate the force within an electric field. When a charged particle moves into the electric field of another charged particle, it is either pushed or pulled depending on the relationship between the two particles. So if they have the same charge, they're going to be repelled or pushed apart. If they have opposite charges, they're going to be attracted and pulled together. And so if you take a look here, we're going to kind of hint at what this looks like here, and we'll talk about it more specifically later. But notice the arrows. The left one there is a positive, and the arrows are pointed away from it. The right one is a negative, and the arrows are pointed towards it. Now, let's suppose a small charged object exists at a particular location. If another charged object were to be brought near that object, a force would be exerted on it according to Coulomb's law. For setting up a field, it is convenient to say that the original charged object is surrounded by what we call an electric field. And the strength of that field is going to vary depending on how close you are to that particular object. Now, the next picture I'm going to show you is going to give you an idea of a field. This is going to be what's called an electric dipole, and we'll talk a little bit more about that later. But I want you to pay attention to the two particles, their relationship to each other, and the field lines that are there. So here is your electric dipole. Notice that in between the two charged particles, there are more lines. The lines represent the strength of the field. As you get further away from the two particles, those lines get more spaced out, meaning that there is a weaker field at those points. But I also want to point out the direction of the arrows. The arrows are going to point from the positive charge to the negative charge. This is the typical setup for how we go ahead and indicate a field. And I'll tell you why here in just a minute. So, a field is actually just a mathematical construct that associates something to every point in space-time. A field takes a value in that thing. Remember that the electromagnetic force, like the gravitational force, is infinite. And as such, two charged particles are interacting with each other no matter where they are in space-time. The field lines simply express the relationship between the two particles at a particular point in space. Okay? So think about that for a second. It's a mathematical construct. Is that a real thing? Or is that something humans have made up to better understand how the system works? And does it matter? So a field is where many possible arrangements of specific values exist in space-time that produce the same physical measurement. Our measurement, in this case, done by Coulomb's law. As such, 20th century physics states that all mathematical descriptions of nature arise from fields. Since these are essentially what we would consider to be equivalent points in terms of the electrical force, according to Coulomb's law, they are equivalent at these points. Is that a real thing? If you want to go down this rabbit hole and kind of explore the idea of whether or not fields really exist, or is this, if a tree falls in the woods and nobody hears it, does it make it sound sort of thing? Um, if you want more information on this or want to explore this a little deeper, please go to the website below at Quora. Do fields really exist? Now, what I'm going to show you are some different examples of electric fields. And I want you to notice that in each case, the arrows on the vectors are pointed towards the negative particle and away from the positive particle. The reason for this is that the field that we create, right, is produced by using what they would call a test particle. And a test particle is going to be a tiny, 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 tiny charge, but it's positive. And so as such, a positive and a positive would repel each other, and a positive and a negative would attract each other. So the field lines go away from the positive, which would be a repulsive force, and towards the negative, which would be an attractive force. Okay, so the closer together the lines are, the stronger the field is, and the higher the value of force in terms of Coulomb's law. Now, in this particular instance, we're looking again at an electric dipole. So you have one positive, one negative, and the lines go between them. But what happens if we change the charge on the particles or change the type of particle that exists? Let's look at some other examples. In this particular example, you have two of the same charged particle. Both are positive, and so you see again, the arrows are pointing away from the positive charge in both sides. There is a gap in between those two charges. Okay. Now, what if we go ahead and change the quantity of charge? We still have our dipole, but it's not a balanced dipole. On the left, you have a negative, which is a single negative. And on the right, you have a positive, but it's twice as big as the charge on the left. So you'll notice that there are more lines coming out of the positive charge because it's stronger. And exactly how many? There are twice as many of the electric field lines. And they don't all loop around to the negative because you're going to match the number of lines to represent the strength of the field. Lastly, I want to show you a different kind of setup. We've been doing point charges, but what if you had a bar charge? Okay, you can see that in this particular instance, we have a positively charged bar on the left and a negatively charged bar on the right, and the electric field lines simply go across it. Okay. Now, we mentioned this a couple of times, and I want to highlight this term just to make sure you understand. The electric field lines due to two equal charges of opposite signs is known as an electric dipole. And these are the most common field lines seen and were the first ones that I showed you. Okay. The strength of an electric field at a certain point is equal to the strength of the force on a charge of 1 Coulomb placed at that point. So the unit of electric field strength is then going to be expressed in the terms newtons per Coulomb, or force per single charge. Once we know the strength of an electric field at any particular point, we no longer need to know the charges that cause the field to know what the force that will be exerted by another charge placed there. Now, let's take an example. Let's suppose that you have a charge of 0.05 coulombs is placed at a point in an electric field where the electric field strength is 250 newtons per coulomb. As such, all you'd have to do is go ahead and multiply your 250 times your 0.05. Coulombs cancel, leaving you with newtons, and now you have a force. That gives you the strength of the force applied to that particular particle if placed there. This is going to be an extension, essentially, of Coulomb's law. So in this particular instance, the electric force is the force per coulomb, and we can go ahead and do this as Q, little q, that's the small charge, um, times big Q, that's the charge of the one creating the field, divided by little q of the smaller particle plus the distance away squared. Okay. Now, let's use that to go ahead and calculate how much electrostatic force would be experienced by a charge of 0.02 coulombs placed at a location where the electric field has a value of 30 newtons per coulomb. All right, so go ahead and pause the video here, go back if you need to use the equation again, and let's go ahead and calculate this out. Okay, so what'd you get? How'd we go ahead and set this up? Let's go ahead and try this. All right, so I'll go ahead and do it yellow, but we'll go ahead and give this a roll. So what we have here is we have a charge and we have a force per charge. So simply to calculate this, we're going to do 30 newtons per coulomb times 0.02 coulombs. Coulombs are going to cancel, leaving us with newtons, which makes sense because we're looking for a force, electrostatic force, electric. And if we go ahead and do the math, that gives us 0.6 newtons. Okay, let's double check that against the work I did last night. There we go. Excellent. Okay. So you can see here that when we go ahead and do this, we are able to make an easy problem solving experience because we already have it in newtons per coulomb. If we know how big the charge is that we're going to go ahead and place into the field, it's pretty simple to go ahead and figure out how much force is on that particular particle. So the electric field can also be written in more practical units. 1 volt is equal to 1 joule per coulomb. Remember, joule is the one that we use to go ahead and do work, and it's equal to 1 Newton meter. By combining the relationship between the units, it is possible to prove that 1 Newton per coulomb is equal to 1 voltmeter. This allows for the creation of electric fields in the laboratory that are very predictable. A voltage difference of 1 volt over a space of 1 meter makes an electric field of 1 voltmeter, which exerts a force of 1 Newton per coulomb for a 1 coulomb test charge. Okay. Remember that the direction E is always away from Q if Q is positive and always towards Q if Q is negative. Thus, a negative Q will produce an attractive force if the field is produced by a positive point charge. Likewise, a negative Q will produce a repulsive force if the field is produced by a negative point charge. So you can see whether or not the particle that you're putting into the field will be attracted to the point or repulsed by the point. Now I have some videos here to kind of go over the structure of an electric field and how we can go ahead and think about space between the space within a field and how it behaves. And I'll let you go ahead and watch that now.
Okay, in today's video, we are going to go over an introduction to the electric field. Now, in this video, we're just going to talk about how to determine the direction and the magnitude, but we're not going to actually calculate any magnitude. I'm just going to go through the equation, and then in the next video, we'll do a few simple electric field calculations. And I think it's important that you watch this introduction video and the next video on doing the calculations to get a good understanding of how the electric field works. It's a little bit confusing, okay? And I think people have a hard time conceptually because we're going to talk about the electric field and then the force per coulomb on a separate charge. So you need to really watch both videos. Now, in this first video, we're going to tell you that by definition, the electric field is the force per unit of charge. And I think the confusing thing is it's which force on which charge. All right? Now, by definition, not by definition, it is a force, so therefore it's a vector, and therefore it has a magnitude and a direction. Now, the first thing we're going to do is talk about the direction. How do we determine the direction of the electric field around this charge? I also want to say that in order to have an electric field, you only need one charge. Every charge has its own electric field. Now, we can have more than one charge and add up the electric fields, but in order to have an electric field, you only need one charge, which is different than Coulomb's law or the electric force. In order to have a force, you need to have two charges. Okay, so this is where it gets a little confusing. There's a little bit of a difference between, or there's really a big difference between the electric force in Coulomb's law and the electric field. And I hope to straighten that out in this video. But I want to point out that we're going to look at the direction first. Now, how do we figure out the direction of the electric field around this charge? Well, what we do is we take out this very special thing called our test charge. The test charge is a very small positive charge. There are two things you need to remember about the test charge. One is it's very small. It's very small in magnitude compared to the main charge, this capital Q main charge. And therefore, it does not really disrupt the electric field of this main charge in theory. Also, the test charge is always positive. So it's positive and it's very small. And what we do is we ask ourselves, if I put this test charge right here, in which direction is the force going to be on this test charge? Well, this is positive and this is positive, so therefore the direction of the force is like that. So we could represent the electric field with an arrow that points away from the charge. Now let's try another test charge over here. What happens? Well, once again, we still have two positive charges. So the force on the test charge is still going to be away from the main charge. Well, let's just try because maybe it's different, like way out over here. Well, once again, it's still positive and positive. So the direction of the electric field, the direction of the force on that test charge is away from the main charge. And you can see basically now if we put a test charge anywhere, because it's positive around that positive charge, that the direction of the electric field is away from the main charge. Okay, and that's how we would draw or represent graphically the electric field, those arrows pointing away from the center of our main capital Q charge. Now, one thing I want to say about the magnitude is we can represent kind of in general, okay, qualitatively, the magnitude of the charge by the magnitude of the electric field by the density of the electric field lines. You can see that here, close to the charge, the lines are relatively close together, whereas here, away from the charge, they're farther apart. That means that here, away from the charge, the electric field is weaker than it is here close to the charge, okay? Because the lines are farther apart. Now, if we wanted to show an increase graphically in the electric field, let's say we wanted to show it doubling, then we would just simply draw twice as many lines like that. That represents a doubling of the electric field. Okay, now let's see what it would look like around a negative charge. Now we're going to do the same thing. We're going to take out our test charge. It's still very small and it's still positive. And because it's positive and this charge is negative, the direction of the force on the test charge is going to be toward the main charge. Well, let's try it over here because maybe, again, well, still towards negative and positive. And let's try it really here close, still towards the charge. And therefore, you can see anywhere around a negatively charged particle, the electric field points towards the charge. Positive away, negative towards, or from the positive to the negative. And that's how you determine the direction of the electric field. Okay? Now, what about the magnitude? All right, once again, here is our charge, and we have it represented, the field, by these lines. Now, I'm just going to give you the equation, and then in a second, we're going to show you how you derive that equation. But I want to point out again, what's different than the electric force. In order to have an electric field, you only need one charge. Every charge has its own electric field. And you can see the equation for the electric field is K, which is still Coulomb's constant, times Q divided by the distance away from the charge. There's just one Q here. Remember, with the electric force, Coulomb's law has Q1, Q2. That describes the force between two charged particles. This just tells the electric field, and you only need to have one charge to have an electric field. Every charge has its own electric field, and you can see the electric field gets weaker as you get away from the charge. Stronger, directly related to the amount of charge, inversely proportional to the distance away from the charge. Now, I'm going to get rid of this equation, and I'm going to show you how we calculated it, and it'll be coming back in a moment, but it's going to disappear like that. Now, we said earlier that the definition of the electric field is the electric force per unit of charge. But what force on what charge? And it's not the force on this charge, and it's not the unit of charge of this charge. It's the force on a different charge that is around or is in the electric field from another particle. This is capital Q. I like to call this the main charge. This is lowercase q. It is the secondary charge that is going to feel the electric force, the amount of force per unit of its charge. So we have the electric field. E is equal to, by definition, the electric force. So we put the electric force per unit of charge. Now you can see I put lowercase q because it's per unit of this charge, which is placed right here away from this main charge. Okay, you remember the equation for the electric field has this big Q in it, but when we have the definition, or another way to calculate the electric field, is just take the electric force at this point divided by the amount of charge placed at this point away from the main charge. Now that means that, and by definition, the electric field is going to have the units of newtons per coulomb. Newtons of force on this charge per coulomb of this charge. Now, we're going to expand this. E is equal to the electric force. This is the equation K, Q, Q divided by D squared. This is Coulomb's law. That's how we calculate the electric force. But now, in our definition here, it's per unit of this charge. So now I'm going to divide this by this charge. Okay, this charge is this charge. This charge is this charge. Well, we're going to divide it by that same charge. And that's going to allow those two charges to cancel out. We kind of cancel those out. You can see now we're left with our previous equation, which we said is E, the electric field. We calculate the electric field by taking K, multiplying it by the charge of this main charge, and then we pick some distance, like this charge is right here, so that's some distance, and then we divide it by the square of the distance. And then we can say that right here, the electric field strength has some strength, some number of newtons per coulomb. Depending on how much charge we put there, then it will feel a certain number of newtons of force. Okay, so that is how we calculate the electric field using this equation. Now there's one other equation that we kind of use, and you can see if we take this one, E equals the electric force divided by the charge, we can actually figure out the force on the charge. All I did was rearrange this, cross multiply it, I get Fe equals Eq. We can figure out the amount of force on this particle if we know the electric force at this point, if we know the electric field at this point and we know how much charge we put there. Okay, now this comes in handy when we have a whole variety of charges. We can figure out the electric field there, and then we can think about, well, what would the force be, or we can calculate what would the force be based on the charge, and we can switch out different charges and get the electric force pretty easily. Okay, so now I said it's a good idea. That's the end of the introduction. I said it's a good idea if you watch the next video where we do a few simple calculations, and that will be helpful for you, I think, also. Okay, so thank you very much for watching. I hope you found that helpful in figuring out the difference between kind of the electric force and the electric field. If you found that helpful, you can give me a thumbs up or a nice comment in the comment section below, and we will see you in the next video. Thank you for watching.
Okay, so the big things to take away from this particular thing are to make sure that we understand the difference between the force, which is a relationship between two particles, and the field, which exists because of one particle. So let's go ahead and write that down just to kind of make sure that we understand that. So the force requires two particles and is a relationship. The field requires one particle. And this is where it gets kind of a little tricky, that whole chicken and the egg thing. This one is a mathematical construct that allows us to go ahead and calculate what that relationship would be, or the force would be, if we were to go ahead and put a particle of a particular charge in that field. Okay, so this is the relationship between the two. And for the field itself, we have a slightly different equation than what we'd use for the force, which, remember, the force, we're going to go ahead and use Coulomb's law that we introduced you to last time. Right? And so the next video is going to go ahead and show you how to go ahead and calculate this, and then we'll go ahead and get towards the end for today. All right. Okay, so let's go ahead and watch that next video. I know it may be a little slow, but there's important and valuable information here.
Okay, in today's video, we are going to do a couple simple electric field calculations. This is going to be example number 1. Now, I did mention in the previous video, which was electric field and introduction, that it would be a good idea if you watch the introduction and then watch this video. The introduction goes over kind of a conceptual understanding of the electric field. This is going to go through a couple calculations. And I think if you watch both, and you can link here to the introduction if you want to watch that first. If you want to watch both the introduction and this example number 1, then I think you will have a good conceptual and mathematical understanding of how the electric field works. Okay, now I just want to point out before we actually do the calculation that the definition of the electric field, once I said before, and it still is, which I wrote down here, is the electric force per unit of charge. I think that's one of the complicating things, is what force on what charge, and I hope to straighten that out in this video. So let's get started. And the question is, what is the magnitude and direction of the electric field if we're 4.52 centimeters to the left of this charge, which is a negative charge and has a magnitude of 8.15?
Okay, so I'm going to try and pause these so you can go ahead and try and solve these as you go ahead and go through. Now, I'm going to let him go ahead and go through this first one so you can kind of see how it works. But then I'd like you to go ahead and, in your notes, go ahead and practice or try these as you're going through before I finish them.
Millicoulombs. M here is for millicoulombs. So we're going to figure out the magnitude and the direction. The direction is pretty easy to do because we're just going to use our positive test charge. We're going to use our test charge, which is always very small and positive, and we ask ourselves, okay, in which direction will the force on this positive charge be? And the direction is going to be to the right if it's 4.52 centimeters away. It's going to be to the right, actually anywhere on the right-hand side here. The force on this test charge is going to be to the right, and therefore that's the direction of the electric field. That's how we define the direction of the electric field. And you should remember, really, around a negative charge, the electric field always points towards the charge. And around a positive charge, the electric field points away. So here, the electric field points to the right, which is different over here. The electric field will point to the left. Okay, now how do we calculate the magnitude of the electric field right here at this point, 4.52 centimeters away? All right, now we use our calculation, or use our equation. The electric field is equal to K, Coulomb's constant, times Q, which is the magnitude of this main charge, divided by the distance away from this main charge. And the distance away is 4.52 centimeters. Okay, you'll notice this equation for the electric field only has one charge in it because every single charge has its own electric field. All right, you don't need two charges to have an electric field. You need two charges to have an electric force, Coulomb's law, but you only need one charge to have a field. Okay, so E, the electric field, is equal to Coulomb's constant, 9 times 10 to the 9th Newton meter squared Coulomb squared, times the magnitude of the charge. We left the negative sign out because this equation we use to calculate the magnitude of the electric field. The direction we got using our test charge to the right. This we use to calculate the magnitude, so we don't put a negative sign in here. It's just the magnitude of the charge divided by the distance, the square of the distance away. Now I want to point out that this was 8.15 millicoulombs. That charge has to be in coulombs when you put it in this equation because the constant is in coulombs. So I just put 10 to the minus 3 because that's what milli is, 10 to the minus 3. 8.15 times 10 to the minus 3 coulombs. Also, the distance has to be in meters, so I converted that 0.0452 meters. I'm going to square the meters and this value, and the meters is going to go away. I only have 1 coulomb. I have Coulomb squared, so one of the coulombs is going to go away. I'm left with newtons per coulomb, and that's the definition of the electric field, newtons per coulomb. So your answer better be a newton per coulomb, and when you do that, you get that the electric field strength, 4.52 centimeters, or that the electric field, 4.52 centimeters, to the left of that 8.15 millicoulomb charge is 3.59 times 10 to the 10th newtons per coulomb, to the right, magnitude and direction. Now, what does that mean? This, I think, is the critical point. Okay, remember the definition of the electric field is that Coulomb is the electric force per unit of charge. So it's the force per unit of charge. Well, the force on what charge? It's the force on a charge that would be placed right here. Any charge. Okay? It's the amount of force per unit of charge. Now, we can rearrange that to figure out how much force. And this is, I think, where we usually talk about this, is how much force would there be placed on a charge at this location. And we would calculate the amount of force by taking the electric field, which is newtons per coulomb, and multiplying it by the amount of coulombs that we put here. And therefore, if you take a coulomb and you multiply it by newton per coulomb, you just get a force. So if I was to put 1 coulomb right here, the force on that 1 coulomb would just be 1 times the electric field, which would be 3.59 times 10 to the 10 newtons. Well, if I was to put 2 coulombs right here, then the force would be 2 times, or 2 coulombs times the electric force, the electric field, and that would be 2 times 3.59 times 10 to the 10th newtons. If I was to put half a coulomb here, then it would be half a coulomb times the electric field, which would be half of this value, 10 to the 5th. Okay, so it's important to remember, this is, I think, the key thing is, it's the amount of force at this location per the amount of charge, per the unit of charge that is placed at this location. It's not the force on this particle that you're really calculating. It's the force here at this location. All right. Now you might say, well, that's the same because they're, they were because of the equal and opposite in Coulomb's law. But if you have a variety of charges, you can figure out the electric field at this location, and then you can figure out the amount of force based on how much charge is placed right there. Okay, now one thing we can use this for is to calculate the acceleration of a particle that is placed right here, or the force. So we're going to do that right now as a kind of application. And we want to know what would be the acceleration of an electron that was placed 4.52 centimeters to the left. So remember, the electric field, we figure out the direction with the test charge. We put a test charge, the force on that charge would be to the right. So the electric field is to the right. But we don't want to know what the electric field is. We got that already. We want to know what the acceleration would be of an electron that was placed right there. So we're going to put an electron there, a minus q, and it's the same location.
Okay, so as he goes ahead and goes through this, what I want you to kind of think about is this idea of now using what you already know about what we learned last semester and what we've just figured out in terms of the electric field to go ahead and better understand how you can really use this equation to place anything into the electric field and find out how it's going to behave.
4.52 centimeters away. And we want to know what the acceleration is. Well, the direction of the acceleration, the direction of the motion, we can get because this is negative and this is negative. So the acceleration is actually going to be to the left. Remember, the electric field was to the right, but the acceleration is to the left because now we have a negative charge. And two negatives are going to repel each other. Okay, now how do we calculate the magnitude of that charge? Well, the magnitude of the acceleration. We're going to use the acceleration equation, which of course the most common one is Newton's second law, but we want to just remind ourselves, we know the electric field at that place right there is this value. We know the charge on the electron is 1.6 times 10 to the minus 19 coulombs. So we're going to use Newton's second law, F equals ma. We want to calculate the acceleration. Well, the acceleration is equal to the force, therefore, divided by the mass. Well, what is the force? Well, the force is really the force due to these two charged particles, which is the electric force, which is Coulomb's force or Coulomb's law. But we're not going to put Coulomb's law in here. Remember from the previous slide, we said that the electric force is also equal to Q, the amount of charge, times the electric field at this location. Okay, now we already know the electric field, so we don't need to go through and calculate the Coulomb force. We know the electric field. So we're going to take this and substitute it in. We're going to put QE right here. So we get that the acceleration is the amount of charge times the electric field, because that's the force, divided by the mass of the electron. And that would be Q, which is, again, 1.6 times 10 to the minus 19, and we don't put the negative sign in. I mean, you could, but you don't need to. It's to the left. We already figured that out. Times the electric field, and we're going to divide that by the mass. The mass of an electron is 9.1 times 10 to the minus 31 kilograms. And you get that the initial acceleration, because of course once it starts to move, it's going to move away and the electric field is going to get weaker. But the initial acceleration at this point of an electron would be 6.31 times 10 to the 21st meters per second squared. Okay? So that's how we can use our electric field calculations. All right, so I think that should give you a good mathematical conceptual understanding about the electric field. Remember, I want to say this one more time. It's the amount of force per unit of charge that is placed right here in this particle's electric field. This particle has an electric field, okay? And the electric field really describes how much force would be applied to this particle that is placed in this other particle, the main particle's electric field. Okay, so thank you very much for watching. I hope you found that helpful. I hope that was clear. If you found that helpful, you could give me a nice thumbs up or a nice comment in the comment section below. Thank you very much for watching. We will see you in the next video.
Okay, so one quick thing I want to point out here that's he doesn't quite kind of go into is this idea of when you put the charge in that you're focusing on the charge of the particle that's there before you put the charge in. Now, I do want you to realize that the force that you're going to feel, and we're calculating it using Coulomb's law and going from there. But technically speaking, by adding the test charge, you're changing the field. Okay, and this is why that the test charge, if we're going to go ahead and set up this electric field, has to be tiny, tiny, because otherwise it's going to go ahead and alter the field noticeably. With it being tiny, it's not going to have a huge impact on what the field looks like in that particular place, and so you can neglect the difference. Okay. So this is how we go ahead and set up these calculations, and it can give us a really good approximation about what's going to happen. But if you put a really large charged molecule into that field or particle, it's going to have greater field on its own than what you just put it into. And so the impact is not going to be the same. All right. So once again, test charges must be tiny, or they alter the electric field. And if you can go ahead and make your way through my horrible handwriting, but I think that's a key point to make sure you take away from this as well. While these are powerful mathematical tools for predicting what's going to happen, the placement of a secondary charge creates a force and actually alters the electric field. And so when we talk about an electric field that has more than one actual particle in it, you're adding those fields together, assuming that the particles aren't moving. But if you have a large enough particle placed into that field, it's going to alter the field itself. And so that's something else I want you to kind of keep in mind. But for all the calculations you'll do in this class, we'll assume that the charge that you're placing is going to be far smaller than any of the charges that are in the field itself. Okay? All right. So let's go ahead and finish up. This actually helps us to understand how current works. Okay? We can now explain how the voltage from a battery causes current to flow in a wire. Once the wire is connected, an electric field spreads very rapidly through the wire, and it spreads so much faster than the electrons can ever move. And because of this, the electrons throughout the wire begin moving and carrying current as soon as they feel the electric field, which is why when you turn on the light switch, the light seems to go on instantaneously. Because as soon as you complete the circuit by turning on the light switch, the loop is closed, the electric field already exists, and the electrons start moving. Now, the electrons move slowly, but the field moves nearly at the speed of light, so it penetrates the entire wire instantaneously. So if you think about what's moving, the electrons are already in place throughout the circuit. And when the field turns on, they begin to move through the circuit. Okay. And when the circuit's turned off and you turn the light switch back off, all the electrons, wherever they move to, simply stop and fall into place. So that when that field gets turned on again, there are plenty of electrons throughout the circuit to just pick up and go ahead and continue moving again. Okay, that's what I've got for you guys today. Stay healthy, stay safe. I'll talk to you soon. Take care of yourselves. Bye bye.